What does it mean to say that two things are independent of each other? That's the topic of this video, and it has strong implications as far as probabilities are concerned. Let's start by thinking of a simple scenario where we draw one card from a standard 52 card deck. One possibility is the card might be a heart. Another is that the card might be a king. Let's let H be the event consisting of all the hearts, and K the event consisting of all the kings. The probability that the card is a heart is 13 out of 52, since there are 13 hearts in the deck, which is 1/4. But also, suppose what happens if you know the card is a king. If you know the card is a king, since the king of hearts is one of the four kings, the chances of getting a heart remains 1/4, even if you know the card is a king. Now let's turn it around. The probability of getting a king is 4 chances in 52, since there are 4 kings in the deck. That's 1/13. But if you know the card is a heart, the chances that it's a king remains 1/13 because one of the 13 hearts is a king. So what we're looking at here is a situation where the chance of one of the things happening is unchanged if you know that the other thing happens. If you know it's a king, it doesn't affect the probability of it being a heart. If you know it's a heart, it doesn't affect the probability of it being a king. This is basically what independence means. Two events are independent of each other if the probability of one of the events occurring is unchanged if you know that the other event occurs. Now, in truth, you don't have to check that going both ways. If one of the conditions is true, then the other will also be true. If the probability of A is the same as the probability of A given B, then it will automatically be the case that the probability of B is the same as the probability of B given A. And furthermore, both of these statements are equivalent to saying that the product of the probabilities is the probability of the intersection. For example, in the last example that we just looked at, the probability of the hearts intersected with the kings is 1/52, since there's only one card which is both a heart and a king, namely the king of hearts. And 1/52 is the product of 1/4, the probability of getting a heart, times 1/13, the probability of getting a king. A good way to intuitively think about independence is to think of independent events as not affecting each other. In other words, whether one of the events occurs has no effect on whether the other one occurs. We'll think about this in the context of tossing a coin twice. The first toss can come up heads or tails, and the second toss can come up heads or tails. Now let's draw our tree so as to reflect the assumption that no matter what has happened before, the chances on each given toss is 1/2 for heads and 1/2 for tails. So if I have a head the first time, then 1/2 and 1/2 are the probabilities for heads and tails on the second toss, and the same is if I have a tail the first time. This, in effect, is an assumption that the first toss and the second toss are independent of each other. If you look at things that way, then the probability of head on the first toss, of course, is 1/2. The probability of heads on the second toss is 1/2. And you get that by seeing that the two cases where head occurs on the second toss each have probability 1/4, so that adds up to 1/2. And if you look at the probability of head on the second toss given head on the first toss, that's in effect 1/2. We've built that into our assumption by putting a 1/2 on this branch in the tree diagram. So the point that I'm making in this picture is that if you draw this tree and put the probabilities in the tree that I have put here, then you're in effect assuming that what happens on the second toss is independent of what happens on the first toss. The probability of getting ahead on both tosses, which is the outcome shown in this slide, is 1/4, and that's equal to the probability of a head on the first toss, which is 1/2, times the probability of a head on the second toss, which is 1/2. Now let's go back to the situation of dealing cards from a deck. Now let's think about dealing 2 cards. And let's keep track with each card dealt as to whether or not the card is a heart. So A will be the event that the first card dealt is a heart, and B will be the event that the second card dealt is a heart. And I want us to think about the intersection of the 2 events. The intersection of the 2 events would simply be the cases where the first card and the second card are hearts, which could be described verbally by saying that it's the event where both cards dealt are hearts. We've looked at this tree diagram in the past. First card may or may not be a heart. Second card may or may not be a heart. And when we looked at this before, we calculated the probabilities by multiplying up along the branches. So this is not a new picture to us. In the context of this picture, let's look at the probability of the event B, which says the second card is a heart. That event would be represented in the tree by the 2 yellow circles. Those are the 2 cases that show the second card being a heart. Their probabilities are 1/17 and 13/68, which is equal to 1/4, which of course is the same that the probability that the first card is a heart. What you have to realize, if your intuition sort of struggles with this, keep in mind that the probabilities shown on these 2 branches, the 12/51 and the 13/51, are the conditional probabilities. On the one hand, the second card being a heart based on the first card being a heart. In the second case, the 13/51, that's the conditional probability the second card is a heart based on the first card not being a heart. So it's pretty obvious what each of those conditional probabilities is if you just think about what's left in the deck of cards after you've dealt a heart or not dealt a heart. But it's not so easy in terms of the tree to think intuitively about what the probability is that the second card is a heart if you don't know any information at all. And what I'm pointing out to you here is that doing the calculation from the tree, you get 1/4 as the answer, which simply says that the probability the second card is a heart is the same as the probability the first card was if you don't know anything about what the first card is. If you don't have any information about the first card, then in terms of probabilities, it doesn't make any difference that that first card has already been dealt. Think about it. So the probability the second card is a heart is 1/4. We just checked that. The probability the second card is a heart, if you know the first card is a heart, is of course 12/51. That's in effect what we were putting in here when we built the tree. A and B are not independent events. The probability of B, if you know that A happens, is not the same as the probability of B based on no information at all. It matters whether the first card is a heart. If you're interested in the probability that the second card is a heart, then it matters whether the first card was a heart. It affects the probability. A and B are not independent events. Whether a heart appears on the first card and whether the heart appears on the second card, these are 2 things that affect each other, so there's no independence here. Now let's picture somebody is throwing darts at a target. And each time they throw a dart at the target, they'll either hit the target or miss the target. And we're going to track them in this tree through 4 throws. So for example, the outcome I'm pointing to would be the case where we have a hit followed by 3 consecutive misses. Now let's suppose every time that this guy throws the dart at the target, there's a 70% chance of a hit and a 30% chance of a miss. If that's true, no matter what has happened before, then it makes the filling in of the probabilities on the branches particularly easy. Just put a 0.7 on every hit branch and a 0.3 on every miss branch. And then any of the outcomes can have their probabilities computed very easily. For example, this outcome which I'm pointing at, which would represent hit, miss, hit, hit, would have as its probability 0.7 times 0.3 times 0.7 times 0.7, because those are the numbers that appear on the branches. Now, notice that there are 4 outcomes in the tree that have exactly that as the probability. They are the 4 brown outcomes, the outcomes represented by the 4 brown circles. Each of those is an outcome where one miss occurred among the 4 throws. In this outcome, we had 3 hits followed by a miss. This outcome shows 2 hits followed by a miss and then another hit. This outcome shows a hit, a miss, and then 2 hits. This outcome shows a miss and then 3 hits. All of those outcomes have 3 hits and a miss, so when you multiply the probabilities of the branches, you're going to have 0.7 occurring 3 times and 0.3 occurring once, just as in the product here. So you're going to get the same product, 0.1049. Those 4 probabilities all added together would be 4 times that, or 0.4116. And if you want to put into words what those 4 outcomes describe, we're looking at all the cases where exactly 3 hits are scored in the 4 throws. So to summarize, by looking at the tree, we have observed that the probability of hitting the target exactly 3 times in 4 tosses is the number shown. The probability of 3 hits in 4 throws we just calculated to be 4 times 0.7 cubed times 0.3. The reason we had a 0.7 cubed is because we were talking about 3 hits, and every time we had a hit, that introduced a factor of 0.7. The reason we have 0.3 raised to the first power is because we're talking about 1 miss. 3 hits in 4 throws means 1 miss in 4 throws. But why the 4? Why do we have the 4 in that expression? When you're talking about 3 hits in 4 throws, the thing to keep in mind is that those 3 hits can occur on any of the 4 throws. So think about how many possibilities there would be for which 3 of the 4 tosses are the tosses where the 3 hits occur. That's simply a counting problem. It's a question of how many different ways could you pick 3 of these 4 boxes as the boxes labeled with the letter H. And the combinations formula gives us 4 as the answer to that counting problem. Now what that line of thinking leads us to is something called the independent trials formula. It's a formula that tells us the exact probability for a certain number of successes and a certain number of trials if we know that the probability of success and failure never change. So the setup is we're doing something over and over. We're repeating the same experiment over and over. And in the independent trials formula, which is stated at the bottom, n represents the number of times we're repeating the experiment. We're talking about 2 arbitrary outcomes called success and failure. We have a success probability P, a failure probability Q, which is 1 minus that. And the basic assumption is that what happens on one trial is independent of what happens on any other trial. The different trials don't affect each other. then the probability of exactly k successes happening during the n trials is given by this product. We have a combinations term, the combination of n things choosing k. We have the success probability raised to the k power and the failure probability to the n minus k power, which would be the number of failures. So let's give some illustrations. First, with a basketball player who's a 70% free throw shooter. Suppose that she attempts 6 free throws during a game. What's the probability she hits exactly 4 of them? We think of hitting as a success in this case. So we're talking about 4 successes in 6 trials. So in the context of the independent trials formula, n is 6, k is 4, combinations of 6 things choosing 4, since the 4 successes, the 4 hits, could be on any 4 of the 6 attempts. 0.7 is the success probability. That's raised to the 4th power because we're talking about 4 hits in 6 attempts. Failure probability raised to the 2nd power, since that means 2 failures in the 6 attempts. So the independent trials formula gives us the probability of that occurring as 0.3241 in this example when you carry out that arithmetic. If a coin is tossed 7 times, what's the probability of exactly 3 heads? If you think of a head as being a success, we're talking about 3 successes in 7 trials. Heads and tails each have probability 1/2, so that's 0.5 to the 3 power and 0.5 to the 4 power. Independent trials formula gives us our probability of exactly 3 heads and 7 tosses, being as shown here. If a die is rolled 6 times, what's the probability of getting exactly 2 sixes? If you think of a 6 as a success, we're talking about 2 successes in 6 trials. A 2 is one of the 6 numbers on the die, so it has 1/6 probability of occurring on any rolls, so that's a success probability of 1/6 to the 2nd power, since we're talking about getting 2 occurrences of that in the 6 rolls. Failure probability 5/6 to the 4th power, since that would mean 4 of the 6 rolls did not result in a 6. Independent trials formula gives us 0.2009 as the answer. If 3 cards are dealt from a standard 52 card deck, what's the probability of getting exactly 2 spades? Think carefully here. This is not an independent trial situation, because when you're dealing cards from the deck, whether one of the cards is a spade would affect the chances of either of the other cards being a spade. So to do this problem, you can't use the independent trials formula. You need to go back and treat it as a counting problem. Getting exactly 2 spades into 3 cards would mean you're getting 2 of the 13 spades and 1 of the 39 cards which are not spades. So this numerator is counting the number of ways to get 2 spades and 1 card which is not a spade. And the denominator counts all the possibilities for getting 3 cards from the deck of 52. Do that division and you get the probability, just as we did back in section 3 of part 5 when we were doing uniform probability distributions. If you tried to do this with the independent trials formula, thinking of 2 successes in 3 trials, spade being a success, 2 spades into 3 cards, I mean, this is what the independent trials formula would lead you to, 1/4 as the probability of a spade on any given card, since 1/4 of the cards in the deck are spades. And of course, that's not quite the same. Now, actually, you could revise this problem a little bit in such a way that it would be the same. If each time you dealt a card, you then put it back in the deck, so that you were each time dealing a card from a full deck of cards, if you did that 3 times and asked what's the probability of getting 2 spades in 3 tries, where every time you're dealing with a full deck of cards, then this would be the correct answer. Because in that case, you're always returning the card to the deck, so what happens on one of the cards does not affect what happens on the next. Suppose now that A and B are independent events, that we know the probability of A is 0.7, probability of B is 0.4. What's the probability of the union? We can get the probability of the union as the sum of the probabilities minus the probability of the intersection. This is one of our early probability properties. And we know the probability of the intersection is just the product of the probabilities if they're independent. That's one of the properties of independence. So we can get the union's probability as 0.7, probability of A, plus 0.4, the probability of B, minus 0.7 times 0.4, the probability of the intersection, resulting in 0.82 is the answer. But remember that doing this calculation does require us to know that the 2 events are independent. Otherwise, we don't know that the probability of the intersection is equal to that product. Now here's an interesting question. It's about airplanes. Suppose that airplane engines operate independently of each other and fail with probability 1/5. Well, I'd hate to fly on an airplane that had that large a probability of failure, but let's give it a shot here and see what we're asking. A plane can fly if at least half its engines work. What's the probability that a plane with 4 engines will crash, and would you be better off flying in a 2-engine plane? Based on this assumption, how can we approach this problem? For a 4-engine airplane, if the engines operate independently and fail with probability 1/5, then the probability all 4 engines work would be talking about 4 successes and 4 trials, if you think about it with the independent trials formula. And the probability of that happening would be the success probability, 1/5 chance of failure, 4/5 chance of success. The success probability raised to the 4th power, because we're talking about 4 engines, 0.4096. Probability exactly 3 of the engines would be working would be talking about 3 of the 4 engines being in a success state. So I'm just literally plugging in the independent trials formula. 3 successes and 4 trials. Success probability 4/5, 3 successes, failure probability to the 1st power because we're talking about 1 engine failing. Probability of exactly 3 working turns out to be the same. And similarly, you can plug into the independent trials formula to get the probability of exactly 2 working to be this number. And all of those cases, 2, 3, or 4 engines working, are cases where at least half of the engines are working if you have a 4-engine plane. So these would be all cases where the plane will fly. Any number of engines less than 2 and the plane doesn't fly because of the assumption that at least half its engines need to work in order for the plane to fly. So if we add up these 3 probabilities, we get 0.9728 as the probability that the plane is able to fly. So the probability of the plane crashing because it can't fly would be 1 minus that, a little over a 2% chance that the plane crashes because of engine failure based on these assumptions when we're talking about a 4-engine plane. Now let's come back and do the computation for a 2-engine plane. If the plane has 2 engines and it will fly if at least half the engines work, that means it'll fly if 1 engine works. The only way it'll crash is if both engines fail. And for both engines to fail, the probability of that happening from the independent trials formula is just 1/5 squared, which is 0.04. So there's a 0.04 probability of crash with the 2-engine plane as compared to the 0.02 something or other with the 4-engine plane. So the answer to part B is no. You would not be better off flying in a 2-engine plane because the probability of crash would be greater. Let's suppose a machine produces parts which are good 90% of the time. So 90% of the parts produced are good. 10% of them are defective. Let's assume each part churned out is independent from all the other parts churned out. So whether one part is good or bad has no effect on whether another part produced is good or bad. First question, what's the probability that a lot of 10 parts contains exactly one defective part? And secondly, what's the probability that a group of 10 parts contains at most 2 defective parts? For the first question, what's the probability that a lot of 10 parts contains exactly one defective part? The probability of one defective means, having one defective means 9 of the 10 parts must be good. So that's 9 successes in 10 trials. 90% of the products are good, so that's a success probability of 0.9 to the 9th power because we're talking about 9 successes. Failure probability to the 1st power. The arithmetic comes out to 0.3874 as the probability of one defective item exactly from the 10 parts. The second question, the probability of 2 defectives would be the probability of 8 good parts. That's 8 successes in 10 trials. So using the independent trials formula, we can easily crank out the probability of that happening. The question, though, says, what's the probability of at most 2 defective parts? So at most 2 means none, 1, or 2. So we have the probability of 2, we have the probability of 1. We need to record the probability of no defective parts, which would be success probability to the 10th power, 0.3487. So all of these probabilities need to be added together, since these are the 3 ways to have no more than 2 defective parts. And the sum of those numbers is 0.930 approximately, which means at most 2 defective is about 93% certain. In this example, we have 2 contestants in a swim meet. They're named Alice and Betty. One of the schools that usually participates in the meet is Claremont. With Claremont participating, Alice has a 20% chance of winning her event, and Betty has a 10% chance of winning hers. And since they're in different events, Alice competes in the butterfly and Betty in the freestyle, whether one of them wins is independent of whether the other one does. Alice winning the butterfly doesn't have any effect on whether or not Betty wins the freestyle. So if we want to look at the 2 swimmers in conjunction with each other, we can put this information into a tree. Alice winning the butterfly has probability 0.2, so not winning would have probability 0.8. So A here represents Alice winning, A complement would be Alice not winning. B represents Betty winning, B complement Betty not winning, and the probabilities I put in are 1/10 for Betty winning, 9/10 for Betty losing, and it doesn't matter whether Alice wins or loses. It has no effect on whether Betty wins or loses, so that's why the numbers at the second level don't change depending on what happens at the first level. Very simple tree, and we can easily get the probability of the 4 possible outcomes. Anne and Betty both win. Alice and Betty both win. Alice wins, Betty loses. Alice loses, Betty wins. Alice loses, Betty loses. So this is all based on the assumption that Claremont participates in the meet. The probability of Alice and Betty winning is the probability Alice wins times the probability Betty wins, because those 2 events are independent of each other. And the probability of Betty winning is unaffected by knowing that Alice wins. So the probability that Betty wins is 0.1, both in the case where Alice wins or in the case where Alice loses. Now, Claremont has some very good swimmers. So if Claremont does not participate, Alice's chance of winning goes way up, and Betty's also. Alice's chance jumps to 80%, which our tree here shows, and Betty's jumps to 60%, which is also shown here. No matter whether Alice wins or loses, Betty now has a 60% chance of winning. So the new probabilities for the four outcomes, based on Claremont not participating, are shown in this tree. And again, the independence still holds up because since they're in different events, whether Alice wins has no effect on whether Betty wins. Now let's suppose there's a 60% chance that the team from Claremont will participate in the meet. How can we factor in this information? Let's draw a bigger tree, which first starts by considering whether or not Claremont participates. A 60% chance they participate, a 40% chance they don't. And then if they do participate, this looks like the first tree that we considered. If they don't participate, then this little piece looks like the second tree that we considered that was based on Claremont not participating. So now by going to a bigger tree that incorporates both of those pieces, we can look at a tree that includes the two cases whether or not Claremont does or does not participate. Based on this larger tree, what are Alice's chances of winning? The four cases that show Alice winning her event in this larger tree would be all the outcomes that pass through this point and which pass through this point. So it would be this case, this one, and this one. Let's describe them verbally. This case is the situation where Claremont participates and Alice and Betty both win. This is the case where Claremont participates in the meet and Alice wins and Betty loses. Claremont does not participate, Alice and Betty both win. Claremont does not participate and Alice wins and Betty loses. Add up the probabilities. We're looking at all the cases where Alice wins, probability 0.44. We can handle Betty in pretty much the same way. The cases where Betty wins are this case, this one, and this one. We add up the four probabilities and we get 0.3 as Betty's probability of winning. Now what's the probability that Alice and Betty both win? These are the two outcomes that are shaded pink in this picture. This pink outcome being the case where Claremont participates and both Alice and Betty win. This one being the case where Alice and Betty, where Claremont does not participate and Alice and Betty both win. Probability of the two pink outcomes adds up to 0.204. We've already computed the probability Alice wins, and we've computed the probability Betty wins. Those two probabilities were determined previously to be these two numbers, and their product is 0.132. So the important thing to focus on here is that the probability of Alice winning times the probability of Betty winning is not the probability of both of those things happening. The probability of the intersection is not the product of the probabilities, which simply says Alice winning and Betty winning are not independent of each other in the context of this tree. Now let's try to understand intuitively how that might be possible, because we already knew that if Claremont did not participate, or if Claremont did participate in either of those two cases, Alice winning and Betty winning were independent of each other. So how is it all of a sudden that by throwing in uncertainty as to whether Claremont will participate, how does that destroy the independence of Alice winning and Betty winning? Think about it like this. Suppose you learn that Alice wins her event. Now remember, Claremont has some very good swimmers. So if you know that Alice wins her event, that might make you think it's pretty likely that Claremont didn't show up for the meet. But if Claremont doesn't show up for the meet, then that's going to increase Betty's chances of winning too, isn't it? Summary. If you know that Alice wins, and you don't know whether Claremont attended, it's going to tend to make you shift your guess as to whether Betty wins higher, shift it to a higher probability, because it would seem to increase the likelihood that Claremont didn't show up for the meet. If you think about it along those lines, I think you can intuitively get a little bit of feel for why, even though they're swimming in different events, they are technically no longer independent events once you include the uncertainty as to whether or not Claremont participates in the meet. Finally, let's move on to an example involving twins. There are two kinds of twins: identical twins, where the twins come from the same egg and therefore they have to be the same sex, or fraternal twins, which come from two different eggs which are separately fertilized. So the sex of one twin is independent from the sex of the other, just as is in the case of separate births. Now, general data on births suggests that 2/3 of twin births are fraternal. So based on that data, let's answer a few questions. What's the probability a set of twins have the same sex? We'll assume here that males and females are equally likely. And secondly, what's the chances that a set of twins are fraternal if you know that they are the same sex? Simple tree for this. Twins have to be either fraternal or identical. If they're identical, they have to be same sex. If they're fraternal, they can be either same sex or different sex. What are the probabilities we're going to put into this tree? Two-thirds and one-third at the bottom level to reflect the data we have that 2/3 of all twin births are fraternal. 2/3 chance of being fraternal, 1/3 chance of being identical. If they're identical, they have to be same sex, probability 1. If they're fraternal, they can either be same sex or different sex. I'm going to put a 1/2 on each of those, and that reflects the fact that we're assuming males and females to be equally likely. So for example, if the first twin to appear was a male, then the second twin, in the case of fraternal twins, would be equally likely to match the sex of the first baby or to be different, no matter whether the first one was male or female. So that means a 1/2 chance that they are the same sex and 1/2 chance that they're different sex. So let's see, based on this tree, what can we calculate? The probability of same sex, since same sex can occur either with identical or fraternal, we add their probabilities and get a 2/3 probability that an arbitrary set of twins will be the same sex. What are the chances of twins being fraternal if we know that they're the same sex? The conditional probability expression shown here requires us to find the probability of their being fraternal and same sex, which we already know is 1/3, that's our numerator, divided by probability of same sex, which we just calculated to be 2/3. 1/3 over 2/3 is 1/2. So based on the knowledge that the twins are the same sex, that means 50% chance that they are fraternal.